Hi. Okay, so we want to talk a little bit about some application of some of the material that we're talking about, and the application is to cryptography, to making secrets. So the first point we want to make is the difference between a code and a cipher. So a code is when you've managed to put the information that you want into some other form. So, for example, here's a famous British sea captain, 1792 to 1848. So you get the sense, of when he lived. So he published a book where in that book every major ship had a number. So there were a small enough number of major ships in the world that every ship in the world had a number, and he that book was available to people, and you would say to a ship, we saw a ship, coming at you, you would say something like, "Show your number," and they would raise up the flag. My number is 4,109, and then you'd know what the ship was. Another example of a code. That's a code. So not a secret, just a code. So another example of a code is the 10 code. So people say 10-4. 10-4 means message received. A 10-20 means location. What's your 10-20? People would say. And the reason for the 10 is that they were invented by the Illinois Police District Number 10, and they published a book with all the 10 codes, and people started using them. So a cipher is an algorithm that's performed on a message's individual letters or small group of letters. The starting material is the plain text, and the ending material is the ciphertext. Your goal is to convert plain text into ciphertext. So we're interested in ciphers, not codes. If we turn words into ASCII and store them in a computer, that's not what we're interested in. That they're encoded, but they're not in some way secret. So they're not encrypted. So to encrypt them, we want to turn plain text, for example, encoded as ASCII, into ciphertext. Okay. So the simplest cipher is the Caesar cipher, which substitutes for each letter in the plaintext a letter some fixed number of positions down an alphabet, and Caesar used the shift of 3. So, for example, if you just represent the letters as A is 0, B is 1, etc., and then you shift by n, then the encryption function is capital E sub n is to take x plus n mod 26. So if, for example, you're shifting by 3 as Caesar did, then you're taking x plus 3. So A would get translated into the plain text. A would get translated into ciphertext. Let's see, A plus 3 is a B, C, D. And then, of course, to decrypt, you just want to subtract. A common thing that you see on the internet is ROT13, which rotates all the letters forward 13 places so that A becomes N, B becomes O, C becomes P, etc. And it's not supposed to be very hard to figure out. The goal instead is to just simply take some text that you don't want to be perfectly obviously available and make it not obviously available. So it's the internet equivalent of a magazine printing the answer to a puzzle upside down. So, for example, if I tell a joke and I want the punchline to be to get to the other side, then I can encode that by using the ROT13 program, rotating everybody by 13, and it gets encoded this way. To decode, of course, I want ROT13 again. That's the advantage of ROT13 is that it's its own inverse. So the encryption function and the decryption function are the same, and so you get back to the original plain text. A very strong method of encryption is to start with a string of random bits, and this is how on Linux you get a string of random bits. You basically go to the random device and you ask to pick out a bunch of random bits, and that's the ones that happen to come up on my computer when I ask for them, and you code your message here by using XOR, exclusive OR, to encrypt. So, for example, here if I say HELP and I put that into ASCII code, that's capital H, that's lowercase e, that's lowercase l, and that's lowercase p. And here I put those random bits that I grabbed off of my computer, and I do the exclusive OR. 1 exclusive ORed with 0 is 1. 0 exclusive ORed with 1 is 1. 0 exclusive ORed with 0 is 0. 1 exclusive ORed with 1 is 0. So I'm doing the exclusive OR of these two lines, the actual ASCII and the random bits, and I'm getting a new string of random bits, and I read them back as though they were ASCII. So this happens to be ASCII G, this happens to be ASCII 3, this happens to be ASCII hash sign, and this happens to be ASCII M. And then I could send G3 hash sign M over the wire. A person who does not have the random bits would be, it's possible to prove, a person who does not have the random bits would be, would be stuck. They couldn't decrypt. So with a string of bits as long as the message, a string of bits that you never reuse, then this is the only provably unbreakable cipher. When you write a string of bits and you want to carry it somewhere, the tradition has been for spies to write it on little books that fit in an easily hideable spot, and so therefore are in your could fit in your hand. They're traditionally hidden under the floorboards of your house, and they're also traditionally written on what amounts to toilet paper. So if somebody catches you, you take your cigarette and you touch it to the book, and the book goes whoof, and it's gone. Flash paper, they call it. So that's a picture of a one-time pad, a string of random bits that was captured from a British spy I think it was the 60s. In this kind of cipher, the string of bits is called the key. So the string of random bits that I came up with from my computer is called the key. It's a symmetric key because you use it both to encode and also to decode. So in practice, you'll often see this naive attempt to encode a string. A program asks you to type in a long string and then converts your string to bits to use as the key. So if you type in, for example, now is the time for all good men to come to the aid of their party, and now that's a bunch of ASCII zeros and ones, and the computer will use those zeros and ones as the key, as what I use, the random bits. And now that's naive, because when the message is longer than the string of bits that you just typed in, what the program will do will cycle around and reuse the message bits. Well, once you reuse the message bits, that's easily breakable. I'm not going to talk about the exact details, but that's easily breakable. So if you see a cipher that advertises itself as very fast, it's likely that it's of this type. It's fast, but it's easily broken. Of course, sometimes, like with RT13, easily broken is not a problem. That perfectly fits within your engineering needs, but nonetheless, that's usually not what they are advertising. So instead, what you need some kind of ciphers that are somehow certified as strong. The Advanced Encryption Standard is a specification for the encryption of electronic data that was established by the U.S. National Institute of Standards and Technology in 2001. It was originally developed by the NSA, the National Security Agency. So here's how I, for example, can encrypt my name here. On the Linux command line, and I have to enter an encryption password. So I entered some encryption password. I'm not going to tell you what it is. I entered some encryption password, and then it asked me, of course, to enter the password twice. And then when I show you the encrypted text, it just looks like garbage. But I can absolutely decrypt by using the D here instead of the A. So I used the D to decrypt, and it asked me to enter the decryption password, and I typed in again. I'm not going to tell you what it is. I typed in, and it gave me back my name. So this is a cipher system, symmetric. You use the same key to decrypt as encrypt. I typed in the same password to decrypt as encrypt. Symmetric, but nonetheless, was considered sort of the standard for many, many years. I can't overemphasize that encryption is very tricky, and the way that I remember that lesson is with Pretty Good Privacy software. So Pretty Good Privacy software, at the time it was written, was illegal, but it made it possible for ordinary people like me to for example, encrypt emails. That's Phil Zimmerman. He's since passed away. He wrote Pretty Good Privacy, which was named after Garrison Keillor type of stuff. So Phil wrote a cipher, and he figured that the way ciphers work is you scramble up the input a whole lot. So you like take the ASCII codes and you flip the back 4 bits to the front, all kinds of stuff like that, scrambling around. He wrote a cipher that scrambled the input, and he called that cipher Bassomatic because of this Saturday Night skit. I'm not going to click on it, but you can click on it yourself. It comes up with the YouTube of that very funny Saturday Night Live skit. He guessed that no one could unscramble it because it seemed to him he had gone through a number of very obscure scrambling steps, but he was a little bit like not perfectly sure. So he showed up, an unknown person, at the 1991 crypto conference, and somebody kindly had lunch with him, agreed to have lunch with him. A lot of people were like, nah, I'm busy, you know. But somebody kindly had lunch with him and immediately he showed them the encryption, and that person said to him, well, you could do this, and you could do this, and you could do this. And so Zimmerman is sitting there saying to himself, there are people in the world who are scarily smart. There are people in the world who it just gives you the creeps how smart they are. So he said, I can't just make something up and figure nobody can break it. I'm going to have to go to a system that experts have agreed is strong. So he switched to an algorithm that had been vetted by people who, for example, people at the crypto conference who had spent years trying to break each other's systems, and this one, wasn't breakable. That people knew at the time. Okay, I want to talk about, now that we have some understanding of what we're doing, I want to talk about the tools that we're going to use to do it. So messages are bit strings. We saw, for example, with HELP, I immediately put it into ASCII code, and there we go. It was strings of bits. So it makes sense to consider them as numerical or at any rate mathematical. So for example, here I took ASDF and I did the magic on it and I got the ASCII for it. And then in that point of view, encoding and decoding are functions. The encoding function takes a bit string in and gives a bit string out. The decoding function takes a bit string in and gives a bit string out, subject to the requirement, of course, that the composition decode after encode is the identity function. Put another way, stated another way, encoding is a one-way function. It would be pretty foolish if both of the messages attack at dawn and wait for another day, encoded to the same output. So we have to have that if you tell me I've encoded the message, here it is, that there's a way to decode it. Otherwise, it'd be pretty foolish. So it has to be the case that the encoding function is one-to-one, because when I go to decode it, I have to get a unique result, namely the original message. Okay, so with that understanding, we're thinking about linear congruences. A linear congruence has the form AX is congruent to B mod M, where A and B and M are numbers. So for example, 8X is congruent to 3 mod 5. And that's an equation, and I can try to solve that for x's. One way to solve for x is to find a number so that a times a hat is congruent to 1. So for example, if I knew what the multiplicative inverse of 8 was, modulo 5, if I knew what the multiplicative inverse of 8 was, modulo 5, then I could multiply both sides by that multiplicative inverse and instantly get x equals whatever it equals. Okay, so for example, suppose I want to solve 3x is congruent to 4 mod 7. And we just note, because we've calculated this in advance, that 5 times 3 is congruent to 1. 5 times 3 is 15, and that's 1 more than 14. 5 times 3 is congruent to 1 mod 7. So if you're given 3x is congruent to 4 mod 7, you multiply both sides by 5. That's one of the rules we saw for modulo arithmetic. You multiply both sides by 5. 5 times 3 gives you the 1x, so you just write down the 1x. 5 times 4 is 20. Modulo 7, that's 6, and we've got our answer. X is 6. So we can solve these systems using the kind of tools of modulo arithmetic if we've paid attention to the tools that we have to use. So under what circumstances can you do that? Can you multiply both sides of the equation by the right number? And the answer is, if a and m are relatively prime, then a has an inverse, modulo m. If a and m are relatively prime, remember what relatively prime means? Means that in the prime factorization, they share no primes. So 3 times 5 is relatively prime to 2 times 7. because they share no primes. Okay, so if A and M are relatively prime, then there's an inverse for A modulo M. Well, we know, because we saw it and we scratched our head over why it's important, because the greatest common divisor of A and M is 1, Euclid's algorithm, remember Euclid's algorithm can be done in reverse from the bottom up? Euclid's algorithm gives a linear combination of the two that adds to 1. S times A plus T times M is 1. So again, Euclid's algorithm, you remember Euclid's algorithm, you take the two numbers and you're going to find the greatest common divisor, and you step, and down at the bottom and you get the greatest common divisor. And we pointed out that you can reverse it to get that the greatest common divisor is a combination of the original two. You go back. All right, that's what we did here. From A and M, we went back to get something times A plus something times M is equal to 1. Now you just have that if it's equal to 1, it's clearly congruent to 1 mod M. Since Tm is a multiple of M, the Tm part is 0. So we're left with SA is congruent to 1 mod M, and that's exactly what we were looking for. We were looking for a number times A is congruent to 1 mod M. And I'm recalling for you that Euclid's algorithm is fast. So what we're doing here is we are coming up with ways to do arithmetic that are fast. When we go to encrypt things, we'll have two criteria. The first is it has to be an uncrackable or relatively uncrackable system. It has to be a one-to-one function. The second is it's got to be fast. So two ways. One is that it has to work. It has to meet the criteria for a good cipher. The second is that it has to be fast. So second point, multiplication modulo M is efficient. Take an integer modulus M, we can do the operation of multiplication efficiently, both in terms of time and also space. So consider, for example, if I want to multiply these, I pick two reasonably large numbers, modulo 3, and I just pick 3, So the naive approach is to multiply 3,915,421 times 52,567,004, multiply them together. This is a naive approach. Multiply them together and then divide by 3 and find the remainder. But I said that's the naive approach. The less naive approach is to first figure out what 3,915,421 is modulo 3. Turns out it's 1. Then figure out what 52,567,004 is modulo 3. Turns out it's 2. And then just multiply 1 by 2. So you can multiply modulo M efficiently. If you give me ridiculously large numbers and you want to multiply them modulo 3, I can do that quickly. So this multiplication is both time and space efficiently. I don't have to store intermediate numbers. When I'm multiplying two numbers in the millions, I'm getting numbers in the, what's 10 to the 12th? Anyway, big numbers. So it takes up a lot of space. But 1 times 2 doesn't take space. That's not a problem. Another thing that's efficient is exponentiation modulo M. So you think exponentiation, you think 4 to the 13 is a hard calculation, but it isn't a hard calculation, not modulo something. For any integer modulus M, we can do the operation of exponentiation efficiently in terms of time and space. So for example, 4 to the 13, modulo 497. The naive approach is to raise 4 to the 13 power, which is a very big number, and then divide by 497 and then figure out what the remainder is. That's the naive approach. Naturally, we're not going to do it that way. Instead, what you do is you express the power 13 in base 2 as 8 plus 4 plus 1. That is to say, you write it in binary as 1101. So that 4 to the 13 is 4 to the 8 times 4 to the 4 times 4 to the 1. Because of the 8, the 4, and the 1. 4 to the 8 times 4 to the 4 times 4 to the 1. Now, here's how I can get 4 to the 13. You start with 4, so you set p equal to 4. Square 4, leave the p alone. So you get 4 squared and you leave the p alone as 4. You square to get 4 to the 4. Multiply that by p to get 4 to the 4 times 4 to the 1. Remember, we want 4 to the 4 times 4 to the 1. Now we've got 4 to the 5. You square 4 to the 4 to get 4 to the 8. Now, all I got to do is take 4 to the 8 times 4 to the 4 times 4 to the 1. So I'm getting here 4 to the 13. But wait, on the last slide, we just said that multiplication modulo any number, 497 in this case, is fast. So these squarings and multiplications here that struck you as, well, okay, you can do it. You can do the Russian peasant method, but it's going to be a big number. All that stuff that struck you as hard stuff is not hard stuff. We just agreed on the previous slide that it's actually easy. That multiplication modulo 497 is actually fast. Cool. Okay, another thing that's fast. So we're working through the operations that are fast because we want to construct our ciphers using fast operations. So the simplest way to test whether a number is prime is to try dividing all the numbers try and divide it by all the numbers less than the square root of it. So for example, if 17 is prime, we say to ourselves, well, we know that 4 squared is 16, so 5 squared is too big, so we don't need to check 5 and on. So we just try dividing 17 by 2. No, no, no. 3. No, no, no. 4. No, no, no. Now, of course, 17 was a toy. 415,693. When you take the square root, you get a number that's a little bigger than 644. Now, I would have to check to 645. But what you see is that 593 times 701 is the actual answer. So we would have to check an awful lot of numbers. 593 is very close to 645. We would have to check an awful lot of numbers to actually find the answer. It is possible to come up with a number and think that maybe it's a prime, and take 593 tries before you find out it's not a prime. To take very nearly the square root of n many tries before you find out it's not a prime. So that's actually a naive approach. That's actually slow. Instead, there's a relatively fast way. So the Fermat's theorem says that for a prime p, if a is not divisible by p, then a to the p minus 1 is congruent to 1 mod p. Excuse me. Excuse me. A to the p minus 1 is congruent to 1 mod p. So we're going to take that as a given statement. Take the prime, for example, to be 7. You look at the numbers between 0 and 7, not including 0, not including 7. So they're obviously not divisible by 7. And we'll look at a to the 6. 1 to the 6, 2 to the 6, 3 to the 6, 4 to the 6, 5 to the 6, 6 to the 6. Remember that exponentiation mod p is very fast. So this is looking fast. When you write it down here and you do it on a calculator, you're like, oh, this is ridiculous calculations. But no, don't forget the previous slide. On a computer, these are fast. Every one of these is congruent to 1 mod 7. 1 is congruent to 1 mod 7. 64 is congruent to 1 mod 7 because 63 is a multiple of 7. 728 is a multiple of 7. 4,095 is a multiple of 7. And I'll let you do the rest. Every darn one of them is a multiple of 7 plus 1. So every one of these is congruent to 1 mod 7. So if you have a number less than p, if p is prime, you expect that that number to the p minus 1 is congruent to 1 mod p. And now if p is not prime, you have no reason to suppose that. But if p is prime, you expect that this statement will be true. So we can get evidence for the primeness of a number by picking a's less than it and calculating a to the n minus 1 modulo n. If you find that the answer is 1, then you're saying could be a prime. If you find that the answer isn't 1, then you say, well, definitely not a prime. So if you keep finding the answer is 1, you're starting to say to yourself, well, this could be a prime. I'm still thinking this is a prime. I'm still thinking this is a prime. Still thinking this is a prime. Okay? So to try to check whether 415,692 were prime, remember that's the number from the previous slide, that we'd have to naively check 593 cases. Instead, we can check 2 to the 415,692, and again, you say to yourself, oh my God, 2 to the 415, that's crazy. It isn't crazy. On a computer, it's very fast. Okay, so we can check 2 to the 415,692, And does it come out to be congruent to 1 mod? No, it does not come out to be congruent to 1 mod 4. So after one calculation, again, a calculation which naively we look at and say, that's a ridiculous calculation, but proves to be, in fact, very fast. So after one fast calculation, we get that this number is not prime. It doesn't take 593 calculations. Instead, it takes one calculation, and we can show that a number is not prime. So we're able to rapidly check whether numbers are prime or not. In a probabilistic primality test, we get confidence of the primeness of the number n. You pick k many numbers between 0 and n, not including 0, not including n, and run the test. If the number passes all of the k many tries, then we're pretty confident that it's prime. Not perfectly 100% sure, but pretty confident. And given that these are fast, we can afford to run a good number of tests. The test is very fast, so just as a very rough break here, we'll ignore these smaller terms and just say it's a k log squared n, roughly speaking, k times log of n, roughly speaking. So very fast. So we could, for example, test that 7 is prime by computing that 3 to the 6 is congruent to 1, 5 to the 6 is congruent to 1, and 6 to the 6 is congruent to 1. That's not all the numbers less than 7, but it's a lot of them. And we can do that very quickly. Again, a person's naive idea here about doing these ridiculous exponentiation calculations is, why would you want to do such a crazy thing? And the answer is because it proves to be fast. Now, the fact that n does not fail any of those 3 times makes us confident that it's prime. So there are numbers that pass all the tests but are not prime. That's possible. Those are called Carmichael numbers. An example of a Carmichael number is 561, but they're very rare. So again, this is a probabilistic test, but we can very quickly become very confident that a number is prime. Okay, a couple more things we want to talk about. Remember that an encryption function, the idea of an encryption function is that plain text goes in, ciphertext comes out, and that the plain text should be easy to turn into the ciphertext. If the encryption function took a very long time, that would be foolish. Related, not perfectly the same, but related is a one-way function, f from the naturals to the naturals, is one where going from the input to the output is easy, but going from the output to the input is hard. So we think of encryption functions as being like one-way functions in that you have to be able to compute the encrypted value quickly. And here, easy and hard means easy in big O terms. So a one-way function should be big O fast. Okay. To encrypt, to get an output, but to go from the output to the input should be big O hard. So just as an example, multiplication is fast, but factoring is slow. I mean, that's kind of the canonical example, is that if we want to multiply 2 numbers, that's very easy. We know fast ways to do that. But if we want to factor a number, if we want to take a number and figure out its prime factors that we know of, that's very slow. So the function that takes as input 2 prime numbers p and q and returns their product can be computed in big O n squared, where n is the total length in bits. But if you want to find the factors of a given integer, n, it runs in exponential time. Look, it's 2 to the log n to the 1/3 log n to the 2. So this is a polynomial in n, but it's not polynomial in the number of bits in n. That is to say, it's pseudo polynomial. In any event, it's slow. Okay. So another example is modular exponentiation can be done in big O n cubed time, but there's no known algorithm to do the opposite, to take the discrete logarithm in polynomial time. So whether true one-way functions exist is not at this time. Nobody has a proof for that, but that doesn't keep people from making them up and working with them. So let's take an example. Passwords on a computer system. So users on a computer system have a password, but you can't store the passwords. Every day there's things on the internet about some, for example, Target or Home Depot get broken into and the password database gets downloaded. So you can't store the passwords. Instead, what the system does is it computes a one-way function, f of the password, and stores that. For example, just as a silly example, we're going to imagine that a user's password is that they require to type in two large primes. So I wrote down two large primes, and then I'm going to store in the password database the product of those two. So I got, got the computer to calculate the product of those two large primes. When I want in, I type in my password, which consists of those two large primes, and the system can rapidly check that when you multiply them together, you do indeed get the number that's stored in the password database. But if a person starts with the password database and tries to decrypt to my two large primes, that we know of, you can't do that. That we know of, that's very, very slow. So we don't think that's feasible. So going one way from input to output is fast. From output to input that we know of at this point is very, very slow. Another example of a one-way function is a digest function. So the ISBN number for a book, for example, everybody has seen the ISBN number. For example, you go on Amazon and you go to order a book, and it'll say the ISBN number of the book. There it is in the graphic. It's down underneath the front cover of the book. So one feature of the standard is that it takes the last digit, so that the total of all the 13 digits is a multiple of 10. That is to say, if you write down if you write down the digits of the ISBN, the first digit, the second digit, all the way up to, it should be the case that first digit plus 3 times the second digit plus the third digit plus 3 times the fourth digit, etc. You do that, it has to come out to be 0, congruent to 0 modulo 10. And for example, there I did the check on the ISBN of my linear algebra book, and it comes out to be 160, and of course that's congruent to 0 modulo 10. So that's a checksum of the ISBN 13. It's a digest. It takes a large amount of information, the 13 numbers that are in the ISBN number. It takes a large amount of information and boils it down to one bit of information. In this case, the very last number. What does it take to make the whole thing come out to be congruent to 0 modulo 10? So if a code is entered incorrectly, then probably it'll catch the incorrect code. The system will come back and say there's no such ISBN. You typed something wrong. So it takes a large piece of information and boils it down to a smaller bit of information. That's called a digest function. So another example of a digest function is we can break a message into, for example, 7-bit words and take the exclusive OR of all those words. Here's a little Python program that does that. It reads in the message, and it takes the exclusive OR of all of the words, and it prints out the result. For example, if I enter my name, then it's adding up all of the, it's finding the bitwise exclusive OR of all of these. It turns out that the bitwise exclusive OR of all of these is right here. Now, that's a digest function. I've taken all this information and boiled it down to a smaller amount of information. If you, for example, typed my name in incorrectly, had only one F, let's say, why then your bitwise exclusive OR wouldn't come out correctly. So this checksum is a little harder to fool than the ISBN checksum. You have to solve a system of equations modulo 2. It's still possible, but it's harder to fool. Now, a hash function, going through a lot of vocabulary words, a hash function maps data of an arbitrarily large size over to a fixed size, subject to the condition that finding two inputs with the same output is infeasible. So with an encryption function, it had to be one-to-one. When you took an input message and encrypted it, you had to get a unique output because you're going to then want to decrypt it back to the original message. But with a hash function, it's not one-to-one. It can't be one-to-one because you're taking arbitrarily large input and you're mapping it to a fixed size. A minute ago, I was taking arbitrarily large input and mapping it to the 7-bit digest function. So we're taking arbitrarily large size to a fixed size, and the only condition is that finding two inputs with the same output has to be very hard. So hash functions give an output that's a digest of the input. That's the point of a hash function. So here's an example I used of a hash function, a standard hash function called SH256, and again, this is the Linux command line that I have to work, and it says take Jim Heffron and send it to this program here, and this is what it takes the string Jim Heffron and turns it into that collection of ASCII letters. letters and numbers, letters and digits. Notice that if I change Jim Heffron to James Heffron, I get a wildly different sequence. That is to say, inputs that are the same leads to outputs that are completely different. Hashes are chaotic in that way. Inputs that are the same lead to outputs that are completely different, and they are of a fixed size. You can have different sizes. I chose the SHA 256, but anyway, the hashes are chaotic. So in particular, it's not possible to say, I've got the first three letters fixed, now all I have to do is get the fourth. It doesn't work that way. You can't say, I got the 02D, now I got to work on getting the A. It doesn't work that way. So, here's, for example, if you go to download Ubuntu 20 from the internet, it'll tell you that we took the Ubuntu 20 binary and we did an SHA 256 hash of it, and here is the result. So then you download Ubuntu 20, and you can run this program on your Ubuntu 20 and check that you got the same hash as the sender promises you'll get. If you didn't get the same hash, why you didn't get the same bits. So you don't need to compare all the bits in Ubuntu 20 to the bits that the vendor says they sent. Instead, you only need to convert to a hash function and check the hash. So you verify your download by seeing if it has the same hash, and this protects you, for example, against man-in-the-middle accounts, attacks, people who see that you're downloading Ubuntu 20 and slip something in the middle while you're trying to download it. So here's an example of using a hash function. And so imagine you have a database of documents. You have a document and you want to see if it's a repeat. Is it already in the database? So to see if two documents are the same, you could compare your document bit by bit to every document in the database, but that would be very slow. Instead, what the database does is pre-compiles their hash, and then all you got to do is compare the hash of your document to the hash of all their documents, and that's fast because the hashes are short. Since hashes allow any length input and have a fixed length output, there's got to be two inputs with the same output. However, starting with an output and finding the associated input has got to be very, very hard. That's pretty much the definition of hash. Conceivable, but not feasible. Even fixing just a small part of the output. If you say, well, look, I want the first three characters in the hash to be, ABC. That's going to be hard. That's going to be an awful lot of work. So here's an example of a Python program that does that. So I'm looking to get, to have a string whose hash has 5 zeros in a row at the start of it. Okay, so I'm creating these strings. It begins with JH and then it has some random integers, and I'm looking to see, do I ever get a hash that begins with five zeros in a row? And here's the output. So for example, if I run the program, the very first random number that it attached to the JH, and it took a hash of it, and it begins with E3, B6, AE2, not 0, 0, 0, 0, 0. The next random integer picked is this, did not get 0, 0, 0, did not. The next random integer is this, did not get 0, 0, did not. So I kept running it until I got 1, 2, 3, 4, 5 zeros in a row. And then, of course, there's all kinds of other junk. But it turns out that if you have the random integer 6033, 2636, and you put a JH on the front, and you take the 256 hash, what you get does indeed start with 5 zeros. It took me, look at this, it took me 2 million tries to find one that began with 5 zeros. So it's a lot of work, not just to find the whole hash, but even if you just want to specify a small portion of the hash, it's a lot of work. So finding an input such that the output starts with 5, 0 is a computational problem that you can do on your computer, but you have to take a long time, 2 million tries, to come up with an answer. Notice that we can tune how much work the problem takes. I can, for example, I can specify the number of zeros as input, and then ask for an output that begins with that number of zeros. So there's the Python program that will do it, and you see that I'm timing it here. If I want the hash to start with 1, 0, it took that amount of time, much less than a second. If I want the hash to start with 2 zeros, it took that amount of time, still much less than a second. 3 zeros is they're about 2/100ths of a second. 4 zeros is about 1/5 of a second. 5 zeros is 1 1/3 seconds. 6 zeros is 57 seconds. 7 zeros is 280. So what you're seeing is that as the number of zeros gets larger, the amount of time starts taking off. Can you see these dots? As the number of zeros at the start of the string gets larger, the amount of time starts taking off. So what we're doing is we're coming up with an example of a problem where we can tune the hardness of the problem. We can tune the hardness. I want 8 zeros. Well, that's going to take you a long time. I want 9 zeros. It's going to take a much longer time. Okay. Okay, so when we come back next time, we'll use this information. In particular, we'll use the fact that things like exponentiation modulo m are fast to put together a practical encryption system that all of us have used every day. Okay, see you then.